Hello and welcome to Homework 4 Part 2. In this part of the homework we are taking a look at a problem in which we are looking at a bar. So this drawing here at the top is just some simple bar made out of some material. And what we are asked to do, first what we're going to do is write code to be able to solve for the temperature profile of the entire bar if we want to apply some amount of heat to the left side and some amount of heat to the right side of either end of the bar, and we want to solve for the temperature profile, so obviously need to plot that to see what the profile looks like. Now, more specifically, by the end of part 2, what we are looking to do is to show that the maximum time step that we can run for this code is 0.5 seconds. So we can't run anything above 0.5 seconds. In other words, we can't look at the temperature profile from 1 second to 2 second to 3 second to 4 second. So we can only use increments of 0.5, and we will show that why once we get to the code. But first here I just wanted to explain what's going on in this problem. So like I said, we want to apply some amount of heat to the left and some amount of heat to the right. However, we're starting with a bar that is at constant temperature throughout. And what we are saying here that I've divided this up into a bunch of sections, and we have this J and this delta X to explain where we are at on the bar, and we can use this in our code to be able to know where we're at in the bar. So this J is just simply we can call it like a length step, so length 1, 2, 3, 4, 5, and this delta X is just simply how far we are on the bar. So if we want to find X, we would just multiply J by delta X. So it's just telling us the location that we're at on the bar. So what we know here is that we're going to refer to this N as the time step, or yeah, I guess we could call it the time step. So at time is equal to 0, like I said, we have a constant uniform temperature bar. So we have 20 degrees Celsius on this end and 20 degrees Celsius on this end. And in between we have 20, 20, 20. It's all constant. Now what we're going to say is that, okay, if at N equals 0, so before we get to N equals 1, right when we start, we're going to apply 50 Celsius here, and we're going to apply 80 Celsius here, and we want to be able to find the temperature profile, again, as a function of time throughout the middle of the bar. So again, it's still at N equals 0, right when we apply this, we still have 20s in the middle. Now at N equals 1, so our first time step, we're going to have 50 and 80. These are both constant on the outside. However, we don't know the temperature profile in the middle, and that's what we want to solve for in Python. And we can do that because we have derived this expression in class, and we can code this in and set up a system of arrays to be able to solve for the temperature profile and then plot that on a plotly graph. So just to go through this expression here, from right to left, or from left to right, this R here is just a parameter, and this parameter is equal to the amount of time that we are using, and we will set this in our code. So the amount of time multiplied by the thermal diffusivity, so obviously that will depend on the material, and divided by delta X squared. Obviously we know what delta X squared is. So we will control this. That is why we're just simply putting it in as a one variable parameter. So what we have here on the left side, we have a bunch of terms that we know. So this is basically this T, J plus 1, comma N. This comma N is at the first time step. So we know everything at the first time step. We know the temperature at J plus 1 N. So this J plus 1 is, again, saying where we are at on the bar. And we have 1 minus 2R, again, we know R. This TJ, again, at the first time step N. And at N, we know everything. We know what's being applied on the left, we know what's being applied on the right, and everything in the middle. And then we have plus R, again, we know R, that is what we are using as, we'll insert that as our parameters. And this temperature at J minus 1, again, we know that because we know everything at N, we know all of the temperatures. And this is all equal to the temperature J, so the position J at N plus 1. So when we add a time step, this is what we're solving for, and we can use this repetitively to solve ultimately for the temperature profile over some amount of time. So what we're going to do is go into Python and write code, and we will graph the temperature profile, and then I will show why it is that we can only use a time step of 0.5 seconds. And if we go anything above that, our answer and our plot will deviate from what actually is going on. So let's go ahead and go into Python. Okay, so now that we are in Python, I have gone ahead and entered two of the things that we will need to be importing, which is numerical Python. I've imported that as NP, and the graphing feature in Python, I've imported make subplots from plotly.subplots. Now next, what I have entered in is just the givens of the problem, or simply our parameters. So alpha, our thermal diffusivity, we will set to 1. dx we will set to 1. dt, we will initially have it at 0.5. Again, our time here. However, we'll come back to this in a minute to see which values we can set here for our dt. And we know that r is alpha multiplied by dt over delta x squared. This T naught here will be our initial temperature, again, since we are looking at a bar that is completely initially at 20 degrees Celsius. I have entered that in, and this T left and T right here I have entered in. I will talk about these in a minute. But first, what I'm going to do is I'm also going to enter in our steps here. So we'll go in steps of 20, and I'm going to first create our T array here. And our T array will be composed of a bunch of values of 20. And what I'm going to do is I'm going to do np.full. And what this does is it will allow us to create an array from our first value to our last value, and we'll be able to set the number of values in that array and what value we want in that array. So we will have 20 values. So we'll have, we can insert n here. And our values here will be, we could either put 20, but since I have the T naught entered in already, we will put that as T naught. So now what I'm going to do is enter in, we're going to code in this bar initially when it's at n equals 0, the entire bar, every temperature value on the bar as an array. So what we want to do is we want to set the very left value in the array to 50 and the very right value of the array to 80 to simulate that bar. So if I go something like t in brackets 0, this will allow us to set the first value in the array, and we will set that to t left, which is 50. And if I go t brackets -1, this will give us the very last value in the array, and we want to set that to t right. So now, if we look at t here, if we look at t, we now have an array of what our bar initially looks like. So now what we want to do is we want to code in the formula that we had derived, which will allow us to solve for the temperature profile, which is this here. So on the left side, what we want to see changing is all the values in the middle. We know that the value on the left and the value on the right will not change. Those are constants, 50 and 80. But we want to see how the middle of the bar, how the material, the temperature changes in the middle of the bar. So this Tn, or this Tj n plus 1, what we want to see changing is everything from t to 1. So the second value, so if you look at t1 and slice it to -1, this is what we get. And you may think, well, -1 means it's the last value. Well, when we slice this array, so when I put this colon here, it gives us the second to last value. So these are all the values that we are looking to see how they change. And what we're going to do is once we put this equation in here, we're going to basically run it through a loop so that it updates, and we we will then plot it, and we can see how the temperature throughout the bar changes over time. So let me delete this here. We will have this on the left. So all the values that we want to see changing. And on the right side, let's go back to our document here. We have R times T J plus 1 comma N. So everything in the matrix, or not in the matrix, in the array, shifted to the right 1. So we will have R times T, and then everything shifted, so we'll start at 2 and end at 0, or we can just end the brackets there. And then from here, we will add, I think it's 1 minus 2 times R. And then this is multiplied by, let's see here, Tj comma N. Well, that's just what we had. It's everything in the middle. So 1 to negative 1. Again, first value, or the second value to the second last value. And this, I'm trying to remember what the last one is here. This is R times Tj minus 1 comma N. So everything shifted to the left 1. So R times T, or not T in brackets, T outside of the brackets. And we will start at 0, or we can just put a colon there. And on the left side, we'll have negative 2. Okay? So we have coded in our formula here, and now what we want to do is essentially run this through a loop so we can have the updated values and plot them. Okay, so now what we're going to do is put this through a loop so our temperature values will update and we can ultimately plot the temperature profile. So if I go for I in some range, we'll go 1 to 500. And I need to make sure that, oops, should be I. Need to make sure that this is indented correctly. And what we're going to do inside of this loop is we're going to say, okay, if our value divided by 25, if the remainder of that is 0, then we are going to plot that on our temperature profile. Otherwise, we're just going to have a whole lot of lines on our plot, and it's going to be hard to decipher what the profile actually looks like. So if we do something like if I gotta do this in parentheses, if I put this percent sign, so if I divided by 25, the remainder here is 0. What we are going to do, I need a colon here, I think, yeah. What we're going to do is then plot that value. So I need to add or set fig equal to make a figure here. So make subplots. Okay. Yeah, no, I think I'm good. So we will add a scatter plot. So fig dot add scatter. We'll need some values for x here, and what we're going to do is, since we have an array of 20 here, is just set x equal to the x value is equal to the length of our steps here, n. So np dot arrange will allow us to do that. Our y will be t, since that is what we are updating, and that's what we want to find, or that's what we want to plot is our temperature values. We will set the mode equal to lines, and we're going to name this name each plot as the I value each time it goes through, so that it will have a value associated with. It'll have the right value associated with it when it goes through the loop. So name is equal to f. And I think, so name, yeah, we have to put I in. Okay. Now, we're just going to update the plot, and this is so it actually gives us the plot. So if I do fig.update layout, I'll give it a height and a width here. Fig.update layout, width set equal to 800, and the height I will set equal to 600. And let's see what this looks like here first. Let's make sure it runs here. So this is what the temperature profile looks like, and it looks like our loop worked correctly. See, we divided by 25 here. Let's see. Our naming looks right. If we go down, if we look at I when it goes through the loop, that would make sense that we have 25, 25, 25. So that looks good. The only thing that we're missing is the initial end value, basically the initial condition that we are given. And that's because when we're running this through, we need to add on the outside our initial plot of t before it gets run through the loop. So I'm going to just copy this. Fig.addScatter, our x equals x, except however our name here will be 0. Oops. What did I do wrong here? X equals x. I think maybe I had to. Yeah, there we go. So I had to update the initial conditions here. So this is our temperature profile here, and this would make sense. This blue line you see that we added here is our initial state. So temperature way on the left is 50. We have all of our 20, 20, 20, 20. And 80 over here. So conceptually this makes sense, and we can see how the values fluctuate in the middle of the bar. So this is right, this is our temperature profile. However, the main point of homework 2 leading into, or homework 4 part 2 leading into part 3 is this time step here. Now you notice that we set it originally to 0.5, and we can go down to 0.2. And you see we get a lot more lines on our plot is what it does. Now we could change, like here, we could change this value here to a lower value. If we went back up to 0.4, we can see how that plays into a factor. But something funny here happens, and this will lead us into part 3, is if I go something like dt is 505, look what starts happening at our graph here. So around where we initially saw our steady state line up here, we start getting like these weird triangles here. And if we go like farther to 0.6, we can see that there is a major error here. So in part 3, we will be showing why the maximum time step that we can allow here for our temperature profile is 0.5. But that will conclude part 2 of this homework. We have successfully plotted the temperature profile for the bar. So thank you for watching.